Hello everyone, hope you guys are having a good virtual day at home today, and let's see if we can learn some stuff while we're at it. So today we're going to start, this is some new content, so while we're reviewing in class and stuff, I'm going to go ahead and start lecturing over some new content. So this is redox reactions. So redox reactions are reactions in which electrons are transferred. Okay? So that's the key thing for a redox reaction. An electron has to be transferred. They're often called redox for short, which I think I just did. And most reactions that occur for energy production are actually redox reactions. So when we're looking at combustion reactions, photosynthesis, when our body is producing energy and stuff like that, electron transport train, all that kind of stuff, these are all redox reactions. A real simple redox reaction is something like this. Let's say we have sodium, solid, okay, and we add in some chlorine gas to it, okay. Balance this. We're going to make some sodium chloride. In this one we have a exchange of electrons. Sodium loses that electron and gives it to chlorine, and it makes sodium chloride. Okay, but before we get too far into redox reactions and how to balance them and what they are, first we need to look at oxidation states. So let's go ahead, and that's what we're going to spend most of today's video looking at, is oxidation states. Or sometimes they're also referred to as numbers. Okay, so now, last year when we were looking at honors chemistry, we talked about charges and stuff like that, and charges on ionic compounds are also going to be the same thing as their oxidation state. So if we take this sodium chloride for an example, okay, we got an ionic compound here, and we know that sodium has a +1 charge. Sorry, if I were to write that actually correctly, it'd be a 1+ charge, and chlorine has a 1- charge. So now those are ionic ions, okay, and the charge on them is also their oxidation state, okay, or oxidation number. Now, the reason that we need to talk about oxidation state instead of just calling it charges is atoms in covalent systems, we'll just go with covalent bonds, also have oxidation states. Okay. So whereas an ion, okay, has an actual charge, an atom in a covalent bond has an assumed charge or an oxidation state. And the reason they have that, it's based on their electronegativity, because there's an unequal sharing of electrons. If we remember back to last year, some atoms want electrons more than other atoms. So when they're in a covalent bond, those atoms that want the electrons more are going to hog it. So let's take an example here. Let's say we have something like HCl. Okay, so hydrogen is pretty easily gives up electrons. Okay, and chlorine on the other hand is pretty electronegative because it's on that far end of it's a halogen. So what happens here is the electrons are actually pulled towards chlorine. Okay, so there's an unequal sharing of the electrons. What that leaves us with is hydrogen has a +1 oxidation state, not a charge because there's a covalent bond because it's still sharing those electrons, and chlorine has a -1 oxidation state. Okay, so it's an assumed charge. It's not a real charge, it's an assumed charge. Okay. So and what oxidation states do is they allow us to keep track of electrons. So it's kind of like a banking system. Okay, so we're going to keep track of who has the electrons and where they're at. So first, let's go over some general rules for oxidation states. Okay, the first rule is this: elements in their elemental form have an oxidation state I'm just going to put oxidate of 0. Okay, this is always true. So if I have something like iron, elemental iron, solid, oxidation state, 0. Okay, elemental oxygen, O2, gas, oxidation state, 0. Neon, gas, elemental state, oxidation state, 0. Any compound, any element, sorry, not compound, any element in its elemental form always has an oxidation state of 0. Okay. Monoatomic ions have an oxidation state equal to the charge, their charge. Okay, we already kind of talked about that a little bit. Another example is if we have a sodium ion, it has a +1 or 1+ charge, so its oxidation state is also 1+. If we have oxide, a 2- charge, well, the charge on that is also the same as its oxidation state. Okay, if you had calcium, it has a 2+ charge. Well, that charge is equal to its oxidation state. So for monoatomic ions, all right, so charged ions that have one atom on them, their oxidation state is equal to the charge on that ion. Where it's different is, now let's take a look in covalent systems. Oh, I have a couple more rules, sorry. So elements, in their elemental state, always have an oxidation state of 0. Monoatomic ions have an oxidation state equal to their charge. Okay, fluorine always has an oxidation state of a 1-. Sorry, I should write that the other way. I should say -1. That's the difference between if it's the negative side in front, or positive sign, it's an oxidation state. If it's behind like this, it actually means it's a charge. Okay, fluorine always has a -1 oxidation state. Okay, because there's nothing that fluorine can bond with that's going to pull the electrons more than it. Okay, so again, if we go back to like a HF, hydrofluoric acid, fluorine is hogging these electrons. It's kind of like, no, I kind of want those more than you do hydrogen. Okay, so it's going to hog it. It's going to have assumed -1 charge, and hydrogen's going to have an assumed +1 charge. All right, there is no element on the periodic table that will pull the electrons away from fluorine, so it's always going to have a -1 charge. Oxygen is almost always a -2. Okay, the exceptions are in peroxides. Like hydrogen peroxide, it's a -1. Right? So fluorine always has a -1, oxygen's almost always a -2, and hydrogen is a +1 oxidation state. Okay. So, and this is in covalent. All of these rules down here, all these rules I just talked about down here are for covalent systems or covalent bonds. And these are the values that we know. So let's take a look at what we can do with this. Let's look at a couple examples here. Let's say we have water, okay, H2O. So this is a molecule, so it has an overall charge of 0. So it's not a charged particle, this is not an ion, okay? But there is an unequal sharing of electrons. So if we were to look at this molecule, okay, draw its loose dot structure, this is kind of what it looks like. And what we know is that oxygen hogs the electrons more than hydrogen does. So it's going to pull those electrons from each one of these hydrogens towards itself, and it's going to give it a -2 oxidation state. Whereas this hydrogen is going to be a +1 oxidation state, and this hydrogen over here is going to be a +1 oxidation state. Okay, now if we add up the oxidation states of all those together, you should notice that you have 1, okay, +1, plus another one, -2, or equal to 0. Okay, and why is it a 0? Well, the overall charge on water is 0, so my oxidation state have to equal up to the overall charge. Let's do another example here. Let's say we have carbon dioxide, so CO2. Okay, another covalent system. Right, if you draw the loose dot structure for this, It looks something like this. Okay. That should be no. Alright. Now, according to our rules, we know that oxygen has a -2 oxidation state. Okay? So oxygen has a -2 oxidation state, and I have 2 of them. Okay, so I have a total of a -4 there. So what's carbon have to be in this case? Well, it has to be a +4. Now, if you notice, carbon wasn't one of our rules up here, right? So what we do is we use our rules, what we know for sure. Fluorine is a -1, oxygen is a -2, hydrogen is a +1. And then we find out what the oxidation states of the other atoms in the compounds are. Okay, let's do one more. Let's say we had something like carbon tetrafluoride, CF4. Okay, so fluorine is a -1 oxidation state, and I have 4 of them. So again, that's going to give me a -4 total charge. So carbon in this case also has a +4 oxidation state. We'll do one more. Let's say we have carbon monoxide. Okay, so oxygen has a -2 oxidation state, and carbon in this case is going to have a +2 oxidation state. It's not going to have the +4 oxidation state that it was having, because if it would, then this would have a +2 charge. But for covalent molecules that aren't polyatomic ions, their oxidation state has to add up, overall of all the atoms, has to add up to the overall charge. So where does something like that differ? Okay, so let's write that out. Make sure you write this in your notes. The sum of the oxidation states must equal the charge on the compound or molecule. Okay, so in this case, so there's all those ones that we're doing, the charge, overall charge, was 0. So the sum of the oxidation states has to, or oxidation numbers, has to equal 0. Let's take one more look at where this might be different. Okay, let's say we have hydroxide. Hydroxide is an OH, okay, and it has a 1- charge. So this is actually a charged particle. Okay, so the oxidation state of these has to add up to that -1. Let's see what we do. We know oxygen is a 2- and hydrogen is a +1. Well, look at that. 2- +1, so that's going to give me a -1 overall oxidation number. Another one, let's say we have nitrate, NO3. Okay. So nitrate has a 1- charge on it. Right, it's a polyatomic ion. So let's determine the oxidation states within this. So oxygen again has a 2- oxidation state, and I have 3 of them. So that's going to give me a total of a -6 oxidation states from oxygen. So what does that mean nitrogen has to be? Well, nitrogen has to be a +5 in order for it to get to that -1 overall. Okay, so oxidation states. All we're doing is we're kind of keeping track of who has control of the electrons. So if we were to look at that, this is just saying, hey, oxygen is having more control over those electrons than what nitrogen was having. Oxygen is having more control over an electron than hydrogen was having. Okay, so the oxidation states have to equal the charge, right? When we have monoatomic ions, the oxidation state is equal to the charge on that ion, right? Elements in their elemental form have an oxidation state of 0. That is always true. Okay? So this is the first step before we start looking at redox reactions. And why is this the first step? Well, if redox reactions are reactions when electrons are transferred, we really need to know where the electrons are at, okay, and what their oxidation states are. So let's take a look back at this first reaction that we had overall up here. Okay, so we have sodium, solid sodium, so its elemental state has a charge of 0. Chlorine in its elemental state, so it has an oxidation state of 0. Now they go into sodium chloride. This is an ionic compound where sodium has a 1+ oxidation state and charge, and chlorine has a 1- oxidation state and or charge. So what we see here is the oxidation state has changed for sodium. It has also changed for chlorine, Therefore, we know electrons have been transferred. So that's what we're going to get into when we're looking at redox reactions. Where are the electrons going? How are they getting transferred? Before we do that, we have to be able to identify and write oxidation states for compounds and atoms within compounds. So that's the first video that we have for redox reactions. Don't forget to like, subscribe, tweet, Snapchat, send out on all social media devices so I can get YouTube famous, make lots of extra money. Maybe I'll give some extra credit. Probably not, but you never know. Have a great day.